So hydrogen oxygen fuel cells, one of the reasons this is in the specification is because it's an up and coming bit of theory. It's something that is important and useful in our use of fuels, as we hopefully all know, because we're running out of fossil fuels, and also they produce loads of pollutants. So when we burn them, when we combust them, so we don't really want to use them if we can. So coming up with a different fuel is really important. And hydrogen is an amazing fuel in terms of the amount of energy you can get out of it. But we don't want to burn hydrogen because that can be extremely explosive. It's also really difficult to carry hydrogen around the country. We'll come to that again in a minute. So we want to try and work out how we can use it. So fuel cells are an example. Fuel cells produce a voltage from reacting a fuel, which is usually hydrogen in a hydrogen oxygen fuel cell, but you can have other fuels in other fuel cells, such as methanol or ethanol, with an oxidant, something that can oxidize, i.e. oxygen. In hydrogen oxygen fuel cells, the fuel hydrogen is supplied continuously along with the oxidant oxygen, so the cell doesn't need to be recharged. I'm just going to highlight this as an advantage of fuel cells over what one would consider to be a normal cell, so a little replaceable battery cell, because if you have got enough fuel, you can continue to supply the fuel, then the battery or the cell, can go forever. In other cells, eventually you run out of metals in solution or the solid metal, and so the battery or the cell runs out of power, stops generating EMF, so stops generating a voltage. So one of the advantages of fuel cells is if you can continually supply the fuel, it can go forever, supposedly. Obviously, continuing to supply the fuel is easier said than done. But it means they don't need to be recharged. You don't have to recharge the cell to get it to work again. You can just keep going. Okay, both electrodes are coated in a porous, so honeycomb structure, or a film of platinum-based material, or what was the other phrase we used? A lattice structure. Again, for the same reason, to increase the surface area. Oops, to increase surface area. The electrolyte that we use can either be an acid or it can be an alkali. So you can either have an alkaline hydrogen oxygen fuel cell or acidic hydrogen oxygen fuel cell. But in both cases, the overall equation is the same. Yay! They both give the same overall cell reaction. So once we have taken into account both half cells, we've added them together and deleted anything that appears on both sides, we get the same half cell, which we're going to look at in a second. This is a diagram that shows an alkaline hydrogen oxygen fuel cell. We know it's alkaline because you can see the OH minus in the middle. So that's what makes it alkaline. That shows that it is alkaline. So I'm just going to pop that in there, alkaline. But let's consider what's happening then at the cathode and the anode, or at each electrode. On the left-hand side, we can hopefully see what is happening. We have got our OH minuses coming up and combining with the hydrogen, H2, that is being input. It therefore is producing water, which we can then remove, and some electrons. The electrons can then pass through whatever it is we're trying to power, the battery, the motor, whatever, the voltmeter, if all we're doing is measuring it, onto the other electrode. And at that electrode, we then get oxygen incoming. It can accept electrons, mix with some water, which should be present as well, to produce OH minus ions, and the OH minus ions can then travel across. Now, this is often a semi-permeable membrane, which allows the water to travel back and forth. Or you can also have water input as well, which we haven't shown here. So it does vary. Again, it depends which diagram you look at and which who's doing the explaining as to whether or not you have water input or whether it's come from the semi-permeable membrane or through the semi-permeable membrane. But we can tell that it is an alkaline fuel cell because of the presence of OH- ions. Hopefully everyone's clear on that. The overall equation, you'll notice, if we combine one half cell and the other half cell, we come up with, and delete things that appear on both sides of the equation, we come up with 2H2 plus O2 goes to make 2 waters. That is our overall reaction equation. And it's possible for both, it's the same as I said for both acidic and alkaline conditions. What else was I going to say? Oh, yes. Which is oxidation, which is reduction? Hopefully you can tell using the half cell equations. There's also a phrase that you learnt at GCSE, which is applicable here if you wanted to use it, but you don't have to. I can see that here we are gaining electrons, so I know this has got to be reduction. Oil rig, reduction is gain. So this has got to be reduction. Notice again, it's on the right. And reduction is happening at the cathode. Reduction happens at the cathode. And oxidation, I can see this is oxidation because it's the loss of electrons. And this is also oxidation. And oxidation happens at the anode. Now, if you can remember, if you wanted to work it out, your cathode is the negatively charged electrode. It's negatively charged because cations, which are positively charged, are attracted to it. So a cathode must be negative to make sure they're attracted to it. And this is the one that's got the abundance of electrons. So this is going to be the negative electrode. Negative electrode. So if you want to work that out, you can therefore tell that that must be the cathode. And then this one must be the positive electrode because it is the one that is removing all of the electrons. So that must be the positive electrode. And the positive electrode is the anode because anions, which are negative, are going to be attracted to it. So you can work it out like that, or you can use the phrase which you probably learned at GCSE, which is an ox and a red cat. You may or may not have learnt it, but anyway, an ox and a red cat. So anode is oxidation, reduction is cathode. Personally, I'm not a massive fan of memorizing that because, again, you then also, as well as memorizing that, you also have to remember that it's talking about oxidation is happening at the anode and it's not talking about anions or anything like that, or, you know, an oxidized product or whatever. So personally, I'm not a massive fan. I'd rather work it out, but you feel free to use it to remember which one's which. If you're unsure in an exam and they haven't asked you to specify which is the cathode and which is the anode, you can just talk about one being positive and one being negative. If you're unsure, if you can work out which one's the positive electrode and which one's the negative electrode, then you can just discuss it as being a positive electrode and a negative electrode. You don't have to then define it as cathode or anode if you don't want to, unless they've explicitly asked for it. Okay, so in this case, I've already said that this is an alkaline oxygen fuel cell. And was there anything else I wanted to say? I don't think so, but I am just going to kind of make sure those are linked together. There we go. Okay, let's think about what have we just, we've just done alkaline, so let's think about acidic. So if you need to do acidic, it's here. So this is that. Sorry, that is where I need to put my line because this is actually still alkaline. So that diagram is not applicable to this slide. So for acidic hydrogen oxygen fuel cells, I find acidic easier. I don't know why. I think because there's fewer water molecules getting in the way. But at the anode, H2 splits into H plus and an electron using the platinum catalyst. Platinum catalyst. The proton exchange membrane, which is the bit in the middle, the semi-permeable membrane, which for alkaline allows the hydroxides across, but for acidic will allow protons across, H pluses. It forces electrode from the anode to the cathode, creating an electric current. That's where we get our cell happening. And then at the cathode, oxygen, O2, joins with the H plus that has traveled across the membrane and an electron to create water, to form water molecules, which is, water is the waste product. Very nice waste product to have, actually, water. Okay, so unfortunately that diagram is not applicable here, but let's think about the equations, or look at the equations, because we've got them on the next slide. So as we've seen before, for an alkaline hydrogen oxygen fuel cell, at the negative electrode, that happens, at the positive electrode, that happens, and the overall cell reaction is the one that we've looked at before, 2H2 gaseous plus O2 gaseous goes to make 2 waters, liquid. And then for an acidic hydrogen oxygen fuel cell, as we said before, it's H2 splits into H plus and electrons, and then the H plus and the electrons join up with water on the other electrode to form, join up with oxygen on the other electrode to form water. But the overall cell reaction is the same for both. If you combine the two, cancel things that appear on both sides, then you can create the same overall cell reaction. Just note, we have specifically used 4 electrons in both cases, so we haven't necessarily got the simplest version. For the negative electrode, for example, for the both cases, if you were to write out the equation, you might choose to write it out with half the stoichiometric value. So 1 H2 plus 2 OH minus goes to make 2 waters and 2 electrons, because that's the simplest balanced equation. We've written it doubled, so that you've got the 4 electrons, so you can see hopefully clearly that when you combine the 2 equations, you can cancel all 4 electrons, the 4 electrons on both sides to come up with the same overall cell reaction for both. But just as a note, you might see it written differently in the half amounts. Same with the negative electrode for the acidic hydrogen oxygen fuel cell. You might see it written as H2 goes to make 2 H plus and 2 electrons, because that's the simplest way of writing the balanced equation. It's the same, all we've done is doubled it, just to make it easier to see that you can cancel the electrons to create the overall cell reaction. Both would be given, multiples of equations are given, unless, as I mentioned loads before with Born-Haber cycles, unless it's explaining a specific process which requires specific molarities. In this case, it doesn't. We're just looking at the ratios. So you could write an equation that shows a multiple, and you would be correct. So if you want to memorize it and memorize it in multiples, that's fine. So both acidic and alkaline conditions give the same overall cell reaction. So that makes it a little bit easier. Okay, let's keep going. We're doing quite well for time, which is nice, I think. Yes, let's keep going. So let's think about our advantages and disadvantages. I have kind of mentioned some of these already before, which is quite nice. But let's just confirm them. So they, not always, they do ask for equations. They do ask for, oxidation and reduction equations and combining them to make the whole cell. But a lot of the time, what they ask about when we talk about hydrogen oxygen fuel cells, because there is such variety out there, is the advantages and disadvantages, because they stay the same no matter what your hydrogen oxygen fuel cell looks like. So advantages to hydrogen oxygen fuel cells, or fuel cells in general. You can apply some of these to fuel cells in general. They're a greener alternative to fossil fuels. So methanol or biofuels you can use in fuel cells are greener alternatives. There are no pollutants formed with a hydrogen oxygen fuel cell, because the only waste product, oh, I nearly dropped my mic, let's put that back. The only waste product formed is water. So that makes it a bit nice. Hydrogen oxygen fuel cells are much more efficient, for example, than combustion engines. because combustion engines, there's a huge amount of heat energy wasted. As you know, engines get ridiculously hot. That's energy that you want to be converting into kinetic energy that's being converted into heat energy. So they're not very efficient. So hydrogen oxygen fuel cells are much more efficient. They're not 100% efficient. They're never going to be, because we've still got friction and gravity and all these things to contend with. But they are more efficient, which is good. Disadvantages, though, and they're quite big disadvantages. Hydrogen is a gas and at room temperature and pressure, and it is explosive. It combusts very quickly. It will go up very quickly. Therefore, storage of hydrogen within your fuel cell and the transport of hydrogen across the country, if we wanted to use hydrogen oxygen fuel cells, for example, to power cars, you'd have to transport hydrogen gas across the country. That is going to be really hard to do. It's going to be expensive. It's going to be potentially dangerous. And we're going to need to put an infrastructure in to transport hydrogen gas across the country. At least when we've got our combustion engines, we're using fossil fuels. Fossil fuels like diesel and petrol can be carried around in tankers, which can be driven up and down the country. We've got infrastructure for that. We don't have infrastructure for moving large tanks of hydrogen gas around. So that needs to be considered. Also, unfortunately, lots of the cells, you might even have recognized it in terms of cells with your phones and other technological things. The production of those cells involves toxic chemicals, which need to therefore be disposed of carefully. There's also the use of all these raw materials, but that's kind of the same with everything. But hydrogen oxygen fuel cells, the platinum catalysts, for example, and the membranes can be made of resources of which we don't actually have that many of anyway. So although hydrogen and oxygen are abundant within our Earth and the atmosphere, the other chemicals are A, toxic, but B, a lot more scarce and a lot less available. So not so useful. That's a disadvantage. Okay, how are we doing for time? 5 minutes. Yay, let's have a go at a question. So have a go at this question and then I will go through it in a second. I'll give you less than a minute, 30 seconds or so to have a go. So with this question, it's asking, in an alkaline hydrogen oxygen fuel cell, the half equations involved are blah, 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 and blah, blah, blah. Oh. I think there's an error there. I don't know if this is the same as what you've got in front of you, but there's an error there. So let me just correct that. It should say, let's do 2, 4, 4, 4. And then that should be 2 O2 plus, no, it shouldn't. It should be just O2 plus 2 H2O plus 4 electrons goes to make our hydroxide, 4 hydroxide. It looks like someone's written the acidic, no, in fact, I don't know what they've done, combined half the acidic and half the alkaline fuel cell equation. So apologies for that. It shouldn't, shouldn't say that. It should say 2H2 plus 4OH minus goes to make 4H2O plus 4 electrons, and O2 plus 2H2O goes plus 4 electrons goes to make 4OH minus. So the question is still, explain how electric current can be generated. In my brain context, I'm thinking hydrogen oxygen fuel cells, so electric chemical cells, specifically hydrogen oxygen fuel cells. The command word is explain. So they're looking for a wordy answer. They're looking for an explanation about where we get electric current from. Electric current is the flow of electrons. So they're looking for where we get the flow of electrons or how that comes about. and specifically within an alkaline hydrogen oxygen fuel cell using the equations that we've been given. So 2 moles of hydrogen split and release 4 electrons. See, this is correct, isn't it? Yeah. Whoops. I don't know if you've got this slide in front of you. Apologies if you don't. Hopefully you've corrected the previous one. If not, maybe just make a quick note to double check when you get the answers later. So an answer you could give would be 2 moles of hydrogen splits and releases 4 electrons. Electrons flow to the positive electrode where they are accepted by oxygen, which combines with water to form OH- ions. This flow of electrons generates electric current. Something along those lines. How are we doing for time? Oh my gosh, we're actually early. Whoa. That's amazing. Okay, apologies for that though. I will make a note that that is wrong so that that can be corrected. Lovely. Okay. We are actually 2 minutes early, so that's exciting. So let's have a slightly longer break. We're going to have a break until 3:15, so that's just 7. No, we're not. Sorry, we're past 3:15 till 3:45, 15:45. That's because I saw the 15. 3:45, so 17 minutes or 16 probably by the time I finish talking. During this break, I'm going to put up. Am I the right one? Yes. During this break, I'm going to put up a link to the survey that you need to fill out. If I can get it up, if I can find it. If you can copy it down so that you can look at it later, or if you can go on to it during the break and fill out the survey, that's absolutely fine. Or if you'd like to wait until the end, so until we've had our final session, which is organic synthesis, then please feel free to do that. I will put the slide up again at the end so that you will be able to fill out the form, the feedback form at the end, and therefore you can make sure you can input your email address to get the answers sent over, etc. So, you see, 16 minutes. Have a lovely break. I'll see you in 16 minutes. We'll come back at 1:45, where we'll finish up with some organic synthesis. Thank you very much.